Interestingly for me, with a background in both single crystals, is the fact that you were able to observe third harmonic generation in not so small nanoparticles. So in the case of the SHG signal, you have investigated these effects, and you've referred to previous work. And the comparison is such that you say that the SHG is really a bulk effect of the entire volume.
Yes.
And you analyze this in a very exquisite way with your polarization detection technique. What about the THG?
Yes, so indeed we were very happy to record such strong signal. And there are one interesting study which is showing that we can expect a high Chi3 tensor when the material has high Chi2 tensor, above 1 picometer per volt. If I remember correctly, it's a paper of Kai, which is cited in my thesis. So it gives us the knowledge that as we have high Chi2 tensor, which was designed by synthesis, we also can expect high Chi3 tensor. So that's why we're expecting, and we're indeed observing, a very efficient third harmonic emission. In terms of polarization response, there is a work which is done in our group by master student Cedric Schmidt. He started also recording a third harmonic polarization curves. So indeed we also can see there that it is also a bulk effect.
You mentioned the paper by one of the co-authors was Mr. Bossart on cascaded effects.
Yes, yes.
You have all have you already, when you wrote this, that was some time ago, have you already discriminated between the processes?
Not yet, yes. As you pointed correctly, there is another paper which poses for us some problems of interpreting our data. Because there is a paper which is showing that we can not only have a third harmonic emission by which employs Chi3 tensor, but we also can have a cascaded, so first, second harmonic generation, and then some frequency generation afterwards. And that this cascaded process can take place in a very small volume. They should not propagate. And for us, it's also a problem because it will also have a third power dependence. So we cannot distinguish cascaded third harmonic from direct third harmonic generation just by measuring a power dependence. And it's still a question, and we need to think how to address it.
You mentioned in your outlook that you propose to look at other materials. Have you already done that? If you work with Chi3 in lithium niobate?
Yes, what we haven't measured the ratio between two emissions, second and third, but for example, we measured emission of potassium niobate, and here you can see examples, which looks very familiar as for bismuth ferrite. So indeed, it's not that just unique property of a bismuth ferrite, it is also observed for another harmonic label, and yeah, it will be interesting to investigate more on this. But the bottom line that this technique can be used not only with bismuth ferrite but also with other materials. So we have done the test with other materials, but we haven't went really in depth in this investigation.
What is the role of the absorption in the UV? Even in BFO, the second harmonic will be absorbed to some extent. What is your opinion on the role of the absorption?
For us, the most important role, which I faced during my research, is that there is a concern regarding climate symmetry condition. Because as I mentioned before, any frequency of excitation should be far from resonance. And in our case, BFO started to absorb, I believe, below 500 nanometers. So indeed, we have a little bit of absorption of second harmonic. And it's poses some question if we can really apply climate symmetry conditions. So in our case, this model still worked quite well. Yeah, so I'm talking about this model, which allows us to transform a general form tensor of rank 3 to a matrix. But indeed, that we need to be very careful of using mathematical model which predict polarization response, for example, from material if we will have a third harmonic emission. And also, it can be quasi-resonant, so we can see that third harmonic can be a little bit enhanced if we have a little bit of third harmonic absorption.
What's the situation with silicon carbide? Silicon carbide has many polytypes. One of them was selected here, and I'm not familiar with all the silicon carbides, but silicon carbide comes in very many forms. There are transparent single crystals. There is black. How absorbing is the silicon carbide you used?
Okay. I believe here is. So we used a silicon carbide provided by Ensavion. It's a carbothermal reduction synthesis, which allows to have a quite big nanoparticles around 150 nanometers with a 3C crystal symmetry structure. In terms of absorption, I don't have a slide here. We have a one photon absorption curves, which are in my thesis. And if I remember correctly, it starts to absorb below 350 nanometers.
Daniel is right, because taking into account different polytypes, you can choose a band gap and avoid. For some polytypes, maybe completely avoid absorption up to 3.2 volts for hexagonal polytype, for example. But of course, maybe study together.
That's actually quite an interesting point. I don't want to monopolize the time.
But in our case, there was no absorption at 400, if I remember correctly. So this is the answer to the question.
I'll ask just one more question, if I may, and then make a comment. Does the absorption play a role in the damage threshold? You have an interesting discussion where I think it's in chapter 7. In tissue imaging, you give all the parameters. You show you are 30% below the damage threshold from the group of Mr. Beaurepaire. Is the damage threshold related to absorption in some way? Do you expect it's the same for EFO, for non-absorbing materials? Because you have fairly high fluxes of photons on those particles and on the cell. So there is a damage threshold for the cells,
yes,
and there is a damage threshold for the material as well.
Yes, indeed. So if I understood your question, first part is related to the biological damage, and this was commented in the paper, because biological damage was described by the group of Beaurepaire for the Drosophila embryo development. And why that paper was interesting for us, because it also described infrared region, around 1.2 micron. And their biological damage is quite different as when we use 800, because a lot of people use a paper of Koenig as a reference of biological damage. But that paper is setting limit around 1 terawatt per centimeter square, and we are about 0.6 terawatts, so we can think that we are quite close, but it is not fair comparison, because paper of Koenig and this 1 terawatt per centimeter square threshold is set for 800 nanometers. and our multi-harmonic detection is done with 1.0. So we're quite safe, in my opinion, in biological. On the biological side, in terms of damaging crystal itself, in my experience, we have never seen the damage during laser raster scanning. So, in my opinion, we have never seen the real ionization or melting of the crystals. It is true that for polarization response measurements, when we focus on one particle for a long time in order to record polarization results, sometimes we should have been careful with the intensities and not to starting to ionizing. But it was easily done with the pulse detection, meaning that not constant radiation, but giving some period to the system to release heat. So in terms of bioimaging, I don't see the problem in terms of high intensity both for crystals and for Boston bioapplication. For material characterization, it is true that we need to be careful. And of course, absorption, more absorption, there is more heat, then we start to melt our crystal. So we want to have as little absorption.
So just one comment before concluding. It's a comment in form of a question. You compared SHG nanoparticle measurements with fluorescence nanoparticles. And when I read your manuscript, I asked myself the question, why wouldn't one want to use fluorescent particles with very long decay times? It would be possible, even in the red, not just for short wavelengths, to have resonance times, of course with the decay, but the resonance time would be on the order of 10 to 20 hours. Has that been done? Is this something that is useful for fluorescence microscopy?
I believe, of course, fluorescence will be always useful, and I don't think that our nanoparticles can completely replace this technique. I believe it is a good complementary technique, so fluorescence will always be a very used observable. It is true that there are fluorescent labels which has very enhanced lifetime and can be used for quite long term. But in my opinion, for studies like stem cell development, which can take weeks, then still it won't be enough. And still we will have another limitation of fluorescence like resonance excitation and incoherent emission if we want to use some coherent techniques for detection. So it is true that there are labels which can mitigate some of the drawbacks of fluorescence like bleaching, but there are another properties of fluorescence that we want to address and to propose a complementary technique.
Well, thank you for your answers, and my final comment will be that I'm definitely going to say the same thing as Luigi said this morning when arrived. I'm going to regret Nambiatrine too. You were probably the second before last PhD student finishing your work with Nambiatrine. So thanks for the many years of wonderful collaboration. I hope we'll have other opportunities soon to work together.
Yeah, thank you, Daniel.
Thank you, Daniel. Okay, so first a general comment. I was happy to be part of the jury, and I read this manuscript with interest. It's well written, and the introduction is quite clear, gives all the context, which is nice. I was interested by the imaging with THT nanoparticles, which is quite original, and so I have a few questions on that. Maybe one general comment before my questions is what you did and what you propose is to use them, the fact that these are TG nanoparticles to detect both SAG and TG to isolate them from the background.
Yes.
But another application would be to, I mean, it's nice to have TG nanoparticles because then you could have two types of labels, SAG, you know, SAG probes labeling one type of structure and TAG probes labeling another one with two functionalization, and this would be very interesting too. But this would require optimizations a bit different from what you did. So I have a few questions. First, would it be, so in your estimations, you get signals, SH signal about 1 order or 2 order of magnitudes higher than TAG in your conditions,
Yes.
between 90 and 40 times higher. Can you, I don't know, comment on a way to increase the THG with respect to the SHG? So there are, well, maybe two sub-questions. First, why did you, how did you come to use these systems, these particle nanoparticles? The optimization was mostly on the Kite2, right?
True. Yes, that is true.
And is there a way to optimize the Kite3 in itself, or? It's not a trap, I don't know.
Something.
Yeah, that's true. That so before we optimize Kite2 for the imaging, in terms of third harmonic generation, usually what is detected is a jump of index of refraction.
Yes.
For example, as, in the case of lipid droplets. So we can think that if we will have a higher index of refraction for our nanoparticles, they will be on surface, we will generate better third harmonic. So we will have another contribution for third harmonic in terms of it. We'll have higher jump of refraction. But as far as I remember, the index of refraction of bismuth rise is already very high, it's around 3.
Okay.
So I don't think that it can be improved even
Okay.
further in this respect.
Well, okay. One thing that maybe could be used is larger particles to start with. I mean, you would optimize both SAG and THG, but here you use particles like a few tens of nanometers in size, right?
No, about 100
100
nanometers.
nanometers. Okay. But the signal scales as a squared volume, so if you double the size, it's still not
Yeah,
too large.
that is true, but there is an important caveat, which was also described in one of your papers, in terms of AP detected of third harmonic.
We come to that later. So, but like, for example, here, now on the instrument, could you boost the SHG a bit more, or you think that you are at the limit of the intensity that you could use?
Intensity of detection, you mean?
Well, I mean, if you want to increase the TH to SH ratio,
Yeah, we can work on with the high intensities.
or shorter pulses, which
Yeah, that is
amounts-
true. It is true.
So here the pulse duration was.
It is around 100 femtosecond. It is a tunable, some mysterious crystal, which they say, but it is around 120 femtoseconds. So it is true that if we will use an OPO, for example, and much shorter pulses, we can achieve higher peak intensities.
And then it will be a trade-off with phototoxicity, but toxicity is not a simple issue at all. So in some cases it's linear, in some cases it's non-linear, in some cases it's a 2-photon or a mix of 2 and 3 photon effect. So in this case, short pulse is good to optimize THG.
Yeah.
So there's probably room to. And so my other set of questions is, if you were to use not SAG plus TAG to isolate particles, but I mean, trying to detect SAG on one channel and TAG on the other to have two labels, could you improve the imaging so as to use other tricks to isolate this from the endogenous signals?
That's a good question. Um, so overall, we are already quite good in terms of eliminated autofluorescence, for example, because first of all, we can use longer wavelengths. This, so there is very little autofluorescence. First of all, and second of all, as high harmonic, second and third harmonics, they are very narrow spectrally. We can use specific filters to eliminate this background.
Yes, yes.
So that's why we were interested in high harmonics. But how to eliminate harmonic signal from another endogenous harmonic
It's
signal?
more difficult.
It's more difficult because
In your experiment here, what's the signal to background ratio, the nanoparticle to collagen, for example?
well, it all depends on the colocalization. So when we colocalize our pixel, they come as another channel. So
Sure.
this is just by color
Yes,
for
but
this
just,
image.
just the signal levels, is it about the same? The signal level from the particles and from
From the
endogenous
collagen,
collagen?
you can see it from here.
Oh, yes.
So here are our nanoparticles and this is collagen. So they are comparable. So if you use only intensity and signal to noise, only using one channel, it is very difficult to separate them.
Well,
And the same for third harmonic. Because just again, even if our labels are brighter than the emission, the endogenous emission in terms of signal per volume, the biological constituents like collagen or lipid droplets, they're big, and they, as you say, they contribute much more because they're much bigger.
yes.
So when we're imaging big areas,